Welcome everybody. My name is Hendrik Makait, and today I present to you my work on rethinking message brokers on remote direct memory access and non-volatile memory. Message brokers have a variety of use cases. In particular, they're used to connect data producing services and stream processing engines. Those engines usually consume the produced data in a sequential fashion, and they need to do so with high throughput and low end-to-end latencies. In general, current message brokers have a producer that publishes data by sending it over to the responsible broker. The broker in turn persists the data in storage, either attached storage on disk or an external storage service. If we want to consume this data, we first have to fetch it from storage to the broker if it hasn't been cached, and then send it from the broker to the consumer. Now this worked nicely when we had slow networks, but if we take a look at modern hardware such as InfiniBand networks and also modern storage technology, we can identify several issues here. First, the architecture is built around message-based communication, and previous research has shown that this is insufficient to benefit from the bandwidth of InfiniBand networks. Second, the data transfer is centered around the broker, and this causes it to be a potential bottleneck. Finally, the data is stored in an append-only fashion, which means that it's stored in the order in which it arrives at the broker. This in turn makes it hard to parallelize data transfer if we want to maintain a certain message ordering. So how does our architecture tackle those issues? First, we have dedicated storage nodes that provide us with large areas of non-volatile memory to store the data and that we can access remotely. The broker now focuses on coordinating and managing the access to this storage rather than the data transfer. So if a producer wants to publish data, it can request a remote location from the broker and then use an RDMA write to directly store the data in the storage node. Similarly, if we want to consume data, we can request its location from the broker and then use an RDMA read to efficiently retrieve it. This has several benefits. First, we now use RDMA-based data transfer, and this helps us to benefit from the bandwidth of InfiniBand networks. Second, as I said, the broker focuses on coordination, not data transfer, so it's less of a bottleneck. Finally, since we use byte addressable storage in non-volatile memory, we can easily parallelize data transfer while maintaining message ordering. Now, if we want to build a protocol around this architecture, we have to take several trade-offs into account. In particular, producers need to trade off the fast and exclusive access to partitions with parallel but shared access and the additional overhead for coordination. Similarly, they need to trade off publish latency with delivery guarantees and their required overhead. Finally, there's several opportunities for interleaving and parallelizing data and control flow here for the protocol and the architecture that we saw on the previous slide. For a quick evaluation, let's take a look at producer throughput of our system compared to Apache Kafka. What we can see here is that Kafka is limited by its own overhead, even if it's writing to shared memory, and is not able to scale with increasing message sizes, while our prototype scales and reaches throughputs of up to 10 gigabytes per second. For consumer throughput, we can see that both brokers do scale with the message size, but only our approach reaches the available bandwidth limit of the underlying InfiniBand network, while Apache Kafka stays well below it. Finally, for the publish latencies, we can see that while both systems spike, our approach in blue consistently outperforms Apache Kafka. So in conclusion, we suggest a broker architecture and protocol that scale up single partition throughput for producers and consumers to exploit modern InfiniBand networks. We also ensure message ordering and delivery by writing to byte addressable locations in non-volatile memory. Finally, we reduce CPU overhead by using one-sided RDMA verbs.